When Voyager 1 launched in 1977, scientists expected it to operate for about 5 years. They planned a grand tour of the outer planets, a quick snapshot of Jupiter and Saturn, and then silence. But here we are, decades later, and Voyager 1 is still transmitting data from beyond the edge of our solar system, a place no human-made object has ever been. It's travelling at 38,000 miles per hour, carrying a golden record with sounds of Earth, messages in 55 languages, and music from across human culture. Right now, it's more than 15 billion miles from home, so far that its radio signals take over 22 hours to reach us, crawling across the void at the speed of light. Most people think Voyager 1 will just keep drifting forever, a silent ambassador floating through the Milky Way until the stars burn out. But the reality is far stranger. The spacecraft's journey isn't a simple straight line into infinity, it's a complex path shaped by gravity, radiation, galactic magnetic fields, and the architecture of interstellar space itself. The probe will encounter regions of space we've never studied, cross invisible boundaries we're only beginning to understand, and eventually face forces that will tear it apart or fling it in directions we can't predict. The question isn't just how far Voyager 1 will go, it's what will happen to it along the way, and what that tells us about the true nature of the galaxy we call home, the heliopause and the boundary of solar dominance. Voyager 1 crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. The heliopause isn't a physical wall, it's the boundary where the solar wind, a stream of charged particles flowing outward from the sun, meets the interstellar medium, the thin gas and dust filling the space between stars. For decades, scientists debated where this boundary would be. Early models predicted it might lie somewhere between 90 and 120 astronomical units from the Sun, each AU representing the distance from Earth to the Sun, roughly 93 million miles. Voyager 1 found it at about 122 AU, confirming that the Sun's influence extends far beyond the planets. The crossing wasn't dramatic. There was no sudden jolt, no visible change. Instead, Voyager's instruments detected a shift in the plasma around it. The solar wind's density dropped sharply, while the density of interstellar plasma increased. The magnetic field changed direction. The energy spectrum of cosmic rays, high-speed particles from outside the solar system spiked upward. These measurements told scientists that Voyager had moved from one realm to another, from the Sun's domain into the galaxies. But crossing the heliopause didn't mean leaving the solar system entirely. The Sun's gravitational influence extends much farther, possibly as far as 100,000 AU, to the edge of the Oort cloud, a spherical shell of icy bodies surrounding the solar system. Voyager 1 is still deep within this gravitational sphere, still bound to the Sun's pull, even though it has left the region dominated by the solar wind. The heliopause is just one boundary among many, and Voyager has thousands of years of travel ahead before it truly leaves the Sun's gravitational grip. The structure of the heliopause itself remains a mystery. Scientists don't know if it's smooth or rippled, static or shifting. Observations suggest it might fluctuate with the solar cycle, expanding and contracting as the Sun's activity rises and falls. Some models predict the heliopause could be asymmetric, stretched in one direction by the motion of the solar system through the galaxy, compressed in another by the pressure of interstellar gas. Voyager 1's data has shown that the boundary is thinner than expected, only a few AU across, but its exact shape and dynamics remain uncertain. Beyond the heliopause lies a region called the interstellar medium, a diffuse gas with a density of only about 1 atom per cubic centimetre. That's a near-perfect vacuum by Earth standards, emptier than anything we can create in a laboratory. Yet this medium fills the galaxy, carrying magnetic fields, cosmic rays, and the faint glow of starlight scattered across space. Voyager 1 is now measuring this environment directly, sampling conditions that have never been observed before. The interstellar medium isn't uniform. It's divided into regions of different temperatures and densities, shaped by supernova explosions, stellar winds, and the motion of the galaxy itself. Voyager 1 entered a region called the local interstellar cloud, part of a larger structure known as the local bubble, a cavity of low-density gas carved out by ancient supernovae. The spacecraft's instruments have detected the magnetic field, threading this cloud, measured its temperature at around 7,000 Kelvin, and found that it contains traces of helium, carbon, and other elements ejected by dying stars. Scientists expected the magnetic field in the interstellar medium to point in a specific direction, aligned with the galaxy's spiral structure. But Voyager's measurements showed something different. The field is tilted, rotated from the predicted orientation by about 40 degrees. This discrepancy suggests that the local magnetic environment is influenced by nearby structures, perhaps the remnants of old supernova shells, or the interaction between the local bubble and surrounding clouds. Voyager 1 is providing the first direct measurements of these fields, data that can't be obtained any other way. The plasma in the interstellar medium is also denser than expected. Models predicted a density of about 0.05 electrons per cubic centimeter, but Voyager measured values closer to 0.08. That difference might seem small, but it affects how the solar wind interacts with the interstellar medium, where the heliopause forms, and how cosmic rays propagate through space. These findings are forcing scientists to revise their models, refining our understanding of the boundary between the solar system and the galaxy. As Voyager 1 continues to move outward, it will encounter changing conditions in the interstellar medium. The local interstellar cloud is just one of many clouds filling the local volume of space, each with different properties. In a few thousand years, Voyager might drift into a different cloud, one with a different temperature, density, or magnetic field. These transitions will be invisible from Earth. Voyager's instruments will have long since failed, but they'll mark the probe's passage through the layered structure of the galaxy, the power supply, and the inevitable silence. Voyager 1's journey is powered by 3 radioisotope thermoelectric generators, or RTGs. These devices convert heat from the radioactive decay of plutonium-238 into electricity. When Voyager launched, the RTGs produced about 470 watts of power. By 2024, that output had dropped to around 220 watts, and it continues to decline by roughly 4 watts every year. This decay is unavoidable. It's a consequence of the plutonium's half-life, the time it takes for half of the radioactive material to break down. Plutonium-238 has a half-life of 87.7 years, meaning the RTGs will lose half their power in that span. The spacecraft's systems require power to operate. The instruments, plasma detectors, magnetometers, cosmic ray sensors each draw electricity. The radio transmitter needs power to send signals back to Earth. The onboard computer, the attitude control system, the data recorders all depend on the dwindling supply from the RTGs. As the power decreases, mission engineers have to make difficult choices about which systems to keep running and which to shut down. They've already begun this process. In recent years, they've turned off heaters that kept some instruments warm, gambling that the electronics can survive the cold. They've reduced the amount of data the spacecraft collects, slowing the rate at which information is recorded. They've shut down instruments that have completed their primary objectives, conserving power for the most critical systems. Each decision buys a little more time, extending Voyager's operational life by a few months or years. Current projections suggest that Voyager 1 will run out of usable power sometime around 2025 to 2030. The exact date depends on how well the remaining instruments tolerate the cold, how much power can be squeezed from the declining RTGs, and which systems the mission team chooses to prioritize. When the power finally drops below a critical threshold, the spacecraft will no longer be able to transmit data. It will fall silent, its radio voice fading into the background noise of the cosmos. But silence doesn't mean death. Even after Voyager 1 stops communicating, it will continue to travel. Its velocity won't change, there's no friction in space to slow it down. It will drift onward, a dark, inert object, carrying its golden record and its instruments into the galaxy. The spacecraft's trajectory is set by the velocity it gained from its encounters with Jupiter and Saturn, and by the Sun's gravity, which will continue to pull on it even as it recedes. The spacecraft's physical structure will endure for a long time. The aluminum frame, the titanium fittings, the copper wiring. These materials are stable in the vacuum of space. There's no oxygen to cause rust, no water to corrode metal. Radiation will gradually degrade some components, particularly the plastics and the golden record's protective cover, but the decay will be slow. The biggest threat is micrometeoroids, tiny grains of dust traveling through space at high speeds. A collision with one of these particles could puncture the spacecraft's body, damaging its structure or its instruments. The probability of such a collision is low but not zero. Interstellar space contains dust grains, remnants of ancient stars and supernovae. These particles are rare. Voyager might encounter only a handful over thousands of years, but even a single impact could be catastrophic. The spacecraft has no shields, no armor. If a grain strikes the fuel tank or the RTG housing, it could rupture the container, releasing plutonium into space. If it hits the radio dish, it could knock the antenna out of alignment, severing the last link to Earth even before the power runs out. The golden record, bolted to the outside of the spacecraft, is particularly vulnerable. The record's cover is made of aluminum, coated with a thin layer of gold to protect the grooves from radiation. But over millions of years, cosmic rays will erode this coating, pitting the surface and degrading the audio and images etched into the disk. Studies suggest the record might remain playable for a few 100 million years, perhaps as long as 1 billion, but eventually the damage will accumulate. The sounds of Earth, the greetings in 55 languages, the music of Bach and Beethoven, all will fade into noise. Once Voyager 1 stops transmitting, we'll lose our direct connection to the spacecraft. We won't know where it is, what it's encountering, or whether it's still intact. The probe will become a ghost, invisible and unreachable, a human artifact adrift in the galaxy. Future civilizations, if they exist, might find it someday. They might decode the golden record, listen to the sounds of a distant world, and wonder about the beings who sent it. Or they might never find it at all. Space is vast, and Voyager is small. Galactic rotation and the long orbit around the Milky Way. Voyager 1 isn't just moving away from the Sun, it's also orbiting the center of the Milky Way, just like the Sun, the planets, and every other object in the galaxy. The Sun completes one orbit around the galactic center every 225 to 250 million years, a period sometimes called a galactic year. Voyager 1 is moving with the Sun on this journey, but its own motion adds a small twist to the path. The spacecraft is traveling at about 17 kilometers per second relative to the Sun, heading roughly in the direction of the constellation Ophiuchus. But relative to the galactic center, its motion is much faster. The Sun itself is moving at about 220 kilometers per second as it orbits the galaxy, and Voyager's velocity adds to this. The result is a complex trajectory, a spiral path that curves through the galaxy as the spacecraft drifts outward from the solar system. Over thousands of years, Voyager 1 will move farther from the Sun, crossing the orbits of distant comets and icy bodies in the Oort cloud, but it will remain gravitationally bound to the galaxy, following the galactic rotation like everything else in the Milky Way's disk. The Sun's orbit isn't a perfect circle. It oscillates up and down relative to the galactic plane, rising and falling every 30 million years or so. Voyager will follow a similar pattern, though its oscillations will be slightly different due to its outward motion. The galaxy's gravitational field will shape Voyager's path in ways that are difficult to predict. The Sun orbits in a region where the gravitational pull of the galactic disk is relatively smooth, but Voyager might drift into regions where the field is more irregular. Nearby stars, giant molecular clouds, and the spiral arms themselves all exert gravitational forces that can perturb the spacecraft's trajectory. Over millions of years, these perturbations will accumulate, nudging Voyager onto a path that diverges from the Sun's. One of the most significant influences will be close encounters with other stars. The Sun passes within 2 light-years of another star every few million years on average, and Voyager could experience similar encounters. If the spacecraft drifts far enough from the Sun, it might pass close to a different star, one that exerts a stronger gravitational pull. Such an encounter could alter Voyager's orbit, accelerating it, slowing it down, or deflecting it in a new direction. The nearest star to Voyager's current trajectory is Gliese 445, a red dwarf located about 17.6 light-years from the Sunday. In roughly 40,000 years, Voyager 1 will pass within about 1.6 light-years of this star. The gravitational interaction will be weak. Gliese 445 is a small star, with only about 10% of the Sun's mass, but it will still have an effect. The encounter might change Voyager's velocity by a few meters per second, a tiny shift that will nevertheless alter its long-term path. After Gliese 445, Voyager will continue to drift, passing other stars at irregular intervals. Each encounter will add a small perturbation, a random nudge that makes the spacecraft's trajectory increasingly unpredictable. Over hundreds of thousands of years, these perturbations will compound, and Voyager's path will diverge significantly from any calculated trajectory. The spacecraft will essentially undergo a gravitational random walk, drifting through the galaxy under the influence of countless small forces. The galaxy's spiral arms will also play a role. The Milky Way's arms are regions of higher density, filled with gas, dust, and young stars. As the solar system orbits the galactic center, it passes through these arms every few 100 million years. Voyager, following a similar orbit, will encounter the arms as well. The increased density within the arms creates a stronger gravitational pull, which can accelerate objects passing through. Voyager might experience a slight boost in velocity each time it crosses a spiral arm, gradually increasing its energy and changing its orbit. But the spiral arms are also hazardous. They contain giant molecular clouds, dense regions of gas and dust where stars are born. These clouds are massive, some containing hundreds of thousands of solar masses, and they exert significant gravitational forces. If Voyager passes close to one of these clouds, the encounter could dramatically alter its trajectory, either capturing the spacecraft into a new orbit or flinging it out of the galactic disk entirely. The most extreme outcome would be ejection from the galaxy. If Voyager gains enough energy from gravitational interactions, it could reach the galactic escape velocity, the speed needed to break free of the Milky Way's gravity. For an object in the Sun's orbit, this velocity is about 550 kilometers per second. Voyager is currently moving at only a fraction of that speed, so ejection is unlikely, but it's not impossible. A rare, strong gravitational encounter, perhaps with a massive molecular cloud or a close stellar flyby, could provide the necessary boost. If Voyager is ejected, it will leave the Milky Way and drift into intergalactic space, a void even emptier than the interstellar medium. The density in intergalactic space is less than 1 atom per cubic meter, a vacuum so complete that matter is almost entirely absent. The spacecraft would travel through this void for billions of years, perhaps eventually reaching another galaxy, though the distances are so vast that this is unlikely within any meaningful timescale. The Oort cloud and the realm of distant comets. Long before Voyager 1 escapes the Sun's gravitational influence, it will pass through the Oort cloud, a vast, spherical shell of icy bodies surrounding the solar system. The Oort cloud is one of the least understood regions of space, a distant frontier that no spacecraft has ever visited and that telescopes can barely observe. Voyager 1 will be the first human-made object to traverse this realm. Though it won't be able to send back any data by the time it reaches the Oort cloud, its power will have long since run out. The Oort cloud is believed to extend from about 2000 AU to as far as 100,000 AU from the Sunday. At its inner edge, the cloud begins beyond the Kuiper belt, the region of icy bodies that includes Pluto and other dwarf planets. At its outer edge, it reaches almost a quarter of the way to the nearest star, Proxima Centauri. The cloud contains trillions of objects, most of them small, less than a kilometer across, composed of water ice, methane, ammonia, and rock. These are the leftover building blocks of the solar system, material that never coalesced into planets, flung outward by the gravitational interactions of the young Jupiter and Saturn. Scientists infer the existence of the Oort cloud from the orbits of long-period comets, objects that fall toward the Sun from the outer solar system on highly elongated trajectories. These comets take thousands or even millions of years to complete a single orbit, and their paths suggest they originate in a distant spherical reservoir. The Oort cloud is that reservoir, a frozen archive of primordial material preserved in the cold of deep space. Voyager 1 is currently about 160 AU from the Sun, far beyond Neptune but still well short of the Oort cloud's inner edge. At its current speed of 17 kilometers per second, the spacecraft will take roughly 300 years to reach the 2000 AU mark, where the cloud begins. From there, it will take another 30,000 years to cross the cloud entirely, emerging on the far side around the year 32,000 CE. The journey through the Oort cloud will be uneventful in one sense. Voyager won't encounter many objects. The cloud is so vast and its members so widely spaced that the average distance between bodies is millions of kilometers. The probability of Voyager striking a comet is vanishingly small, far lower than the chance of a micrometeoroid impact in interstellar space. The spacecraft will likely pass through the cloud without coming within 1 million kilometers of any significant object. Yet the Oort cloud is not entirely empty. It contains not just comets, but also the influence of the Sun's gravity, which dominates this region. The cloud marks the boundary of the Sun's gravitational sphere of influence, the region where the Sun's pull is stronger than that of nearby stars. At the outer edge of the Oort cloud, around 100,000 AU, the Sun's gravity weakens to the point where passing stars can perturb the orbits of comets, sending them inward toward the inner solar system or outward into interstellar space. Voyager 1 will experience this boundary directly. As it moves through the Oort cloud, the Sun's gravity will continue to pull on it, but the force will weaken with distance. By the time Voyager reaches the outer edge of the cloud, the Sun's gravitational influence will be 1,000 times weaker than it is at Earth's orbit. The spacecraft will still be bound to the Sun, it's not moving fast enough to escape, but the bond will be tenuous, easily disrupted by external forces. One such force is the gravitational pull of passing stars. The Sun moves through the galaxy at about 220 kilometers per second, and it encounters other stars regularly on cosmic timescales. Every few million years, a star passes close enough to the solar system to perturb the Oort cloud, stirring the orbits of comets and potentially sending some of them into the inner solar system. Voyager, being part of the outer solar system, will be subject to these same perturbations. If a star passes within a few light years of the Sun, its gravity could alter Voyager's trajectory. A distant pass might cause only a small deflection, changing the spacecraft's velocity by a few meters per second. A closer encounter could have a more dramatic effect, potentially boosting Voyager's speed enough to push it onto a trajectory that takes it out of the Oort cloud and into interstellar space. In rare cases, an extremely close pass within a light year or less could even eject Voyager from the solar system entirely, unbinding it from the Sun's gravity. The Oort cloud is also affected by the galactic tide, the differential gravitational pull exerted by the Milky Way. The galaxy's gravity is stronger on the side of the Oort cloud closer to the galactic center and weaker on the far side. This difference creates a tidal force that gently stretches the cloud, pulling some objects outward and pushing others inward. Over millions of years, the galactic tide can destabilize the orbits of Oort cloud objects, sending them on new trajectories. Voyager 1 will experience this tidal force as well. The effect is weak, only a few millimeters per second squared of acceleration, but over thousands of years it will accumulate. The spacecraft's orbit will gradually shift, its path curving slightly, as the galactic tide nudges it in one direction or another. The exact effect depends on Voyager's position relative to the galactic center, which changes as the solar system orbits the Milky Way. Radiation and the slow erosion of components. Space is not empty, it's filled with radiation. Cosmic rays, high-energy particles accelerated by supernova explosions and other violent events, stream through the galaxy at nearly the speed of light. These particles strike everything in their path, including Voyager 1, depositing energy and causing damage at the atomic level. Over decades and centuries, this radiation will gradually degrade the spacecraft's materials, wearing away its structure and eroding its components. Cosmic rays consist mostly of protons, the nuclei of hydrogen atoms, but they also include heavier nuclei like helium, carbon, and iron. When these particles strike a solid object, they penetrate deep into the material, colliding with atoms and knocking them out of place. This process, called radiation damage, creates defects in the crystal structure of metals and semiconductors, weakening their mechanical properties and altering their electrical characteristics. Voyager 1's electronics are particularly vulnerable. The spacecraft's computers, built in the 1970s, use integrated circuits made from silicon and other semiconductors. Cosmic rays can create defects in these materials, disrupting the flow of electrons and causing errors in data processing. The spacecraft's designers anticipated this problem and included radiation-hardened components, but even these have limits. Over time, as the cumulative dose of radiation increases, the electronics will begin to fail. The spacecraft's power supply, the radioisotope thermoelectric generators, will also be affected. The RTGs rely on thermocouples, devices that convert heat into electricity using the Seebeck effect. Cosmic rays can damage the thermocouples, reducing their efficiency and lowering the power output. This effect is small compared to the natural decline caused by the decay of plutonium-238, but it adds to the overall degradation. The spacecraft structure, its aluminum frame, its titanium fittings, its copper wiring, is more resistant to radiation damage but not immune. Metals can suffer from radiation-induced embrittlement, a process where the accumulation of defects makes the material more brittle and prone to fracture. Over millions of years, this embrittlement could weaken Voyager's frame, making it more susceptible to damage from micrometeoroids or thermal stress. The golden record, mounted on the outside of the spacecraft, will also suffer. The record's protective aluminum cover is coated with a thin layer of gold, which shields the grooves from radiation. But cosmic rays will gradually erode this coating, pitting the surface and exposing the aluminum underneath. Once the aluminum is exposed, it will oxidize not from oxygen, which is absent in space, but from reactions with trace amounts of water ice or other volatile compounds that might accumulate on the spacecraft's surface over millions of years. The grooves of the record, which contain audio and images encoded in analog form, are etched into a copper-plated disc. Cosmic rays will damage this copper, creating defects that distort the signal. The higher the cumulative radiation dose, the greater the distortion. Studies suggest that the record might remain playable for a few 100 million years, but the quality will degrade over time. The audio will become noisy, the images indistinct. Eventually, the information will be lost entirely, eroded by the relentless bombardment of cosmic rays. The rate of radiation damage depends on the environment Voyager 1 encounters. In the interstellar medium, the flux of cosmic rays is relatively constant, producing a steady dose of radiation. But if Voyager passes through regions of higher density, such as a molecular cloud or a supernova remnant, the radiation levels could spike. Molecular clouds contain magnetic fields that can trap and accelerate cosmic rays, increasing their energy and intensity. Supernova remnants are even more extreme, producing shocks that accelerate particles to energies millions of times higher than typical cosmic rays. If Voyager 1 passes through such a region, the radiation dose could increase by orders of magnitude. The spacecraft's electronics might fail rapidly, and its structure could be damaged. The golden record could be scarred, its grooves obliterated by high-energy particles. In the worst case, the spacecraft could be torn apart, its components scattered across space. But such encounters are rare. Most of the galaxy is relatively benign, and Voyager will likely spend most of its journey in the quiet interstellar medium, where the radiation dose is low and the damage accumulates slowly. Over millions of years, the spacecraft will gradually decay, its materials weakening, its components failing, its structure eroding. The process is inevitable, a consequence of the laws of physics and the nature of space, magnetic fields and the galactic dynamo. The Milky Way is threaded with magnetic fields, invisible lines of force that pervade the galaxy and shape the motion of charged particles. These fields are generated by the galactic dynamo, a process similar to the one that creates Earth's magnetic field. In the galaxy, the dynamo is driven by the rotation of the galactic disk and the motion of ionized gas within it. As the gas moves, it carries the magnetic field with it, stretching and twisting the field lines and amplifying the field strength. The strength of the galactic magnetic field is weak by terrestrial standards, only a few microgauss, about a millionth of Earth's field. But over the vast scales of the galaxy, even such weak fields can have significant effects. They influence the motion of cosmic rays, guiding them along field lines and preventing them from escaping the galaxy. They shape the structure of the interstellar medium, organizing gas into filaments and sheets. They play a role in star formation, supporting molecular clouds against gravitational collapse. Voyager 1 is now traveling through these fields. The spacecraft's magnetometer, one of its still functioning instruments, has measured the magnetic field strength in the interstellar medium and found it to be about 3 to 4 microgauss. This is slightly higher than previous estimates, suggesting that the local field is stronger than the galactic average. The field is also oriented in a specific direction, roughly aligned with the plane of the galaxy but tilted at an angle. As Voyager moves through the galaxy, it will encounter regions where the magnetic field varies in strength and direction. Near the galactic plane, where the density of gas and stars is highest, the field is stronger and more organized. Above and below the plane, in the halo, the field is weaker and more chaotic. Voyager's trajectory takes it slightly above the galactic plane, so over thousands of years, the spacecraft will drift into regions of weaker, less ordered fields. The magnetic field affects the motion of charged particles, but Voyager 1 is electrically neutral. It carries no net charge. The field doesn't exert a force on the spacecraft itself, but it does affect the environment around it. Cosmic rays, which are charged, follow the magnetic field lines, spiraling along them as they travel through space. This means that the flux of cosmic rays Voyager encounters depends on the local field configuration. In regions where the field is strong and well ordered, cosmic rays are guided along the field lines, and the flux might be higher. In regions where the field is weak or tangled, cosmic rays diffuse more freely, and the flux might be lower. These variations will affect the radiation dose the spacecraft receives, and by extension, the rate at which its components degrade. The magnetic field also plays a role in the propagation of shocks and waves through the interstellar medium. Supernova explosions, stellar winds, and other energetic events generate shock waves that travel through space, compressing the gas and amplifying the magnetic field. If Voyager encounters one of these shocks, the spacecraft might pass through a region of enhanced magnetic field and elevated radiation. The shock itself won't harm the spacecraft, it's far too diffuse, but the associated increase in cosmic ray flux could accelerate the degradation of Voyager's components. The galactic dynamo is not uniform. It operates most efficiently in the galactic disk, where the rotation is fastest and the gas density is highest. In the halo, the dynamo is weaker and the magnetic field is more irregular. Voyager's trajectory takes it into the lower halo, where the field structure is less well understood. The spacecraft's measurements, made during its brief operational period, provided only a snapshot of the field at one location and one time. Future observations, if any, will reveal how the field varies as Voyager moves through different regions of the galaxy. One intriguing possibility is that Voyager could encounter a magnetic field reversal. On Earth, the magnetic field occasionally flips, with the north and south poles swapping places. The galactic magnetic field might undergo similar reversals, though on much longer timescales, millions of years rather than thousands. If Voyager is travelling during a period of reversal, it might pass through regions where the field is weak or chaotic, with field lines pointing in random directions. Such a configuration could affect the motion of cosmic rays and alter the radiation environment. Stellar encounters and gravitational perturbations. The Sun is not alone in its journey through the galaxy. Every star is in motion, orbiting the galactic centre at its own speed and on its own path. The Sun's neighbours change over time, as stars drift past each other like ships in the night. Over millions of years, the Sun will encounter thousands of stars, some passing close, others far away. Voyager 1, travelling outward from the Sun, will experience its own stellar encounters, independent of the Sun's motion. The nearest star to the Sun is Proxima Centauri, about 4.24 light-years away. But Proxima is not on a collision course with the solar system, it's moving at an angle, and over time, it will recede. The next close encounter will be with Gliese 710, a red dwarf currently about 64 light-years away. In about 1.3 million years, Gliese 710 will pass within about 1 light-year of the Sun, close enough to perturb the Oort cloud and possibly send a shower of comets into the inner solar system. But Voyager 1 won't be around to see that encounter. By then, the spacecraft will be far from the Sun, thousands of AU away, possibly even farther. Its first significant stellar encounter will be with Gliese 445 in about 40,000 years. At that time, Voyager will pass within 1.6 light-years of the star, a distance of about 10 trillion kilometers. The gravitational pull of Gliese 445 is weak. The star has only about 10% of the Sun's mass, but over the distance of the encounter, it will exert a measurable force on the spacecraft. The effect of this encounter can be calculated using Newton's law of gravitation. The change in Voyager's velocity will be small, on the order of a few meters per second, but this small change will accumulate over time. The spacecraft's trajectory will curve slightly, and its future path will diverge from the one it would have followed without the encounter. Over hundreds of thousands of years, as Voyager experiences more stellar encounters, these small perturbations will add up, making the spacecraft's long-term trajectory increasingly unpredictable. The probability of a very close encounter within a few astronomical units is extremely low. Stars are widely spaced and the galaxy is vast. Voyager would have to be extraordinarily unlucky to pass within the planetary system of another star. But if such an encounter did occur, the consequences could be dramatic. The gravitational pull of the star could accelerate Voyager, increasing its velocity and sending it onto a new trajectory. If the encounter is close enough, the spacecraft could be captured into orbit around the star, becoming a permanent resident of a new solar system. More likely, Voyager will experience a series of distant encounters, each one altering its trajectory by a small amount. Over time, these perturbations will cause the spacecraft's orbit to drift, its path curving through the galaxy in a complex, unpredictable pattern. The exact sequence of encounters depends on the positions and motions of nearby stars, which are constantly changing. Predicting Voyager's trajectory beyond a few million years is essentially impossible. Stellar encounters can also affect the spacecraft's orientation. Voyager is not actively stabilized, it's not firing thrusters to maintain a specific attitude. Instead, it's slowly tumbling, its orientation changing as it drifts through space. A close stellar encounter could exert a torque on the spacecraft, altering its rotation rate or axis. Over time, these torques will cause Voyager to spin faster or slower, and its antenna might point in a random direction, no longer aligned with Earth. The distribution of stellar encounters is not uniform. In the galactic disk, where the density of stars is higher, encounters are more frequent. In the halo, where the density is lower, encounters are rare. Voyager's trajectory takes it into the lower halo, where it will spend long periods without encountering any stars. These quiet intervals will alternate with periods of higher activity, when the spacecraft passes through denser regions or crosses the galactic plane. Some stellar encounters might involve binary or multiple star systems. About half of all stars in the galaxy are part of binary systems, where two stars orbit each other. If Voyager passes through such a system, the gravitational interactions become more complex. The spacecraft could be slingshot out at high speed, or it could be captured into a chaotic orbit, swinging back and forth between the two stars. The outcomes of such encounters are difficult to predict, and depend sensitively on the spacecraft's initial trajectory and the configuration of the binary system. The influence of giant molecular clouds. Giant molecular clouds are among the largest and most massive structures in the galaxy. These clouds, composed mostly of molecular hydrogen, can span hundreds of light years and contain the mass of millions of suns. They are the birthplaces of stars, regions where gravity compresses the gas into dense cores that eventually ignite nuclear fusion. But they are also gravitational obstacles, capable of deflecting the trajectories of objects that pass nearby. Voyager 1's path through the galaxy will eventually bring it into the vicinity of one or more giant molecular clouds. These encounters are infrequent, the clouds are rare, and the spacecraft's trajectory doesn't necessarily intersect them. But over millions of years, the probability of an encounter becomes significant. If Voyager passes close to a cloud, the cloud's gravity will exert a force on the spacecraft, altering its velocity and trajectory. The gravitational pull of a giant molecular cloud is substantial. A cloud with a mass of 1 million solar masses, located 50 light-years from Voyager, would exert a force strong enough to change the spacecraft's velocity by tens of meters per second over the course of the encounter. This change might not seem large, but it can have a significant effect on Voyager's long-term trajectory, especially if the spacecraft is already on a borderline path between remaining bound to the galaxy and escaping into intergalactic space. The encounter with a molecular cloud is not instantaneous. The cloud is enormous, and Voyager takes thousands of years to pass through its gravitational influence. During this time, the spacecraft's trajectory curves gradually, its path bending as it responds to the cloud's pull. The exact trajectory depends on the cloud's mass, size, and density distribution, as well as Voyager's initial velocity and direction. Molecular clouds are not static. They are dynamic structures, evolving over millions of years as they collapse under their own gravity, fragment into smaller clumps, and eventually form stars. The internal structure of a cloud is complex, with dense cores embedded in a diffuse envelope. If Voyager passes through a dense core, the gravitational pull will be stronger, and the deflection will be more pronounced. If it passes through the envelope, the effect will be weaker. Some molecular clouds are part of larger complexes, regions of the galaxy where multiple clouds cluster together. The Orion Molecular Cloud Complex, for example, contains several giant molecular clouds and spans over 100 light-years. If Voyager encounters such a complex, it might experience a series of gravitational perturbations, each one altering its trajectory in a different way. The cumulative effect could be substantial, potentially sending the spacecraft onto a completely new path. Molecular clouds also affect the interstellar medium around them. They generate winds, shocks, and turbulence that ripple through the surrounding gas. These disturbances can create regions of enhanced density and temperature, which in turn affect the propagation of cosmic rays and the structure of the magnetic field. If Voyager passes through one of these disturbed regions, the spacecraft might encounter elevated radiation levels or magnetic field strengths different from those in the ambient interstellar medium. Another consequence of encountering a molecular cloud is the possibility of increased dust density. The density of dust in a cloud is much higher than in the surrounding interstellar medium, and Voyager might encounter a significantly increased flux of dust particles if it passes through a cloud. These particles, travelling at high speeds relative to the spacecraft, could cause damage if they strike Voyager's structure or instruments. The probability of a direct collision with a dust grain is still low. The particles are small and widely spaced, but the risk is higher in a molecular cloud than in the open interstellar medium. A collision with a large grain, 1 millimeter or more in diameter, could puncture Voyager's body or damage the golden record. Smaller grains might erode the spacecraft's surface, gradually wearing away the aluminum and gold coatings. The galactic disk oscillations and vertical motion. The Sun's orbit around the galactic centre is not confined to a single plane. Instead, the Sun oscillates up and down relative to the galactic midplane, crossing it every 30 million years or so. This vertical motion is driven by the gravitational pull of the galactic disk, which acts like a restoring force, pulling objects back toward the midplane when they drift too far above or below it. Voyager 1 will follow a similar oscillatory pattern, but with a twist. The spacecraft is moving outward from the Sun, and its trajectory is tilted relative to the solar system's plane. This means Voyager's vertical oscillations will be different from the Sun's, with a different amplitude and period. Over millions of years, the spacecraft will rise and fall, crossing the galactic plane multiple times as it travels through the galaxy. The amplitude of Voyager's oscillations depends on its initial velocity perpendicular to the galactic plane. Calculations suggest that the spacecraft's vertical motion will take it several hundred light-years above and below the midplane, possibly as much as 1,000 light-years at the extremes. These excursions will carry Voyager through different environments, from the dense, star-filled regions of the disk to the sparse, diffuse regions of the halo. Near the midplane, the density of stars and gas is highest, and the gravitational pull is strongest. Voyager will move more slowly in this region, its trajectory curving as the disk's gravity pulls it back toward the plane. Above and below the plane, in the halo, the density drops sharply and the gravitational pull weakens. Voyager will move more freely here, its trajectory straightening as the restoring force diminishes. The galactic disk is not perfectly flat. It has a thickness about 1,000 light-years in the thin disk and several thousand light-years in the thick disk. Voyager will spend most of its time within this thickness, crossing back and forth between the thin and thick disks as it oscillates. Each crossing will expose the spacecraft to different conditions, different stellar densities, different radiation levels, different magnetic field configurations. The oscillations also affect Voyager's exposure to supernovae. Supernovae are more common in the galactic plane, where massive stars, the progenitors of supernovae, are concentrated. If Voyager spends more time near the plane, it has a higher probability of being exposed to a nearby supernova. Conversely, if it spends more time in the halo, the probability decreases. The exact risk depends on Voyager's trajectory and the distribution of massive stars along its path. Each time Voyager crosses the galactic plane, it experiences a slight deceleration. The disk's gravity pulls on the spacecraft, slowing its vertical motion and eventually reversing it. This process is analogous to a ball thrown upward, which slows, stops, and falls back down under Earth's gravity. For Voyager, the throw is the spacecraft's initial velocity perpendicular to the plane, and the fall is the return trip as the disk's gravity pulls it back. The period of these oscillations is long tens of millions of years, but the effect is measurable. Over time, Voyager's oscillations will damp out slightly, as energy is dissipated through gravitational interactions with stars and clouds. The spacecraft's vertical motion will become more gradual, and the amplitude of the oscillations will decrease. Eventually, after hundreds of millions of years, Voyager might settle into a more stable orbit, confined closer to the galactic plane. But this is a distant future, far beyond the timescales relevant to the spacecraft's physical survival. Long before the oscillations damp out, Voyager's components will have decayed, its structure will have eroded, and the spacecraft will be nothing more than a cloud of atoms drifting through the galaxy. Supernova remnants and high-energy environments. Supernovae are among the most violent events in the universe. When a massive star exhausts its nuclear fuel, its core collapses, triggering an explosion that releases as much energy in a few seconds as the Sun will emit over its entire lifetime. The explosion blasts the star's outer layers into space, creating a rapidly expanding shell of hot gas and debris. This shell, called a supernova remnant, can persist for thousands of years, glowing brightly in X-rays and radio waves as it sweeps through the interstellar medium. Voyager 1 might encounter a supernova remnant during its journey through the galaxy. These remnants are not rare. There are thousands of them scattered across the Milky Way, the relics of stars that exploded over the past few tens of thousands of years. Some are young, still expanding at thousands of kilometers per second, their shells bright and well-defined. Others are old, their shells faded and dispersed, blending into the background interstellar medium. If Voyager passes through a young supernova remnant, the consequences could be severe. The shell of the remnant is a shock front, a region where the gas is compressed and heated to millions of degrees. The density inside the shock is higher than in the surrounding medium, and the radiation levels are elevated. Cosmic rays, accelerated by the shock, stream outward at nearly the speed of light, creating a zone of intense radiation. The radiation dose inside a supernova remnant can be orders of magnitude higher than in the ambient interstellar medium. If Voyager enters such a region, the flux of cosmic rays striking the spacecraft will increase dramatically. The electronics, already weakened by decades of cumulative radiation damage, might fail rapidly. The structure could be degraded, and the golden record could be scarred by the intense bombardment. But the probability of such an encounter is low. Supernova remnants are large, often tens of light years across, but they are also rare and widely spaced. The average distance between remnants in the galaxy is hundreds of light years, and Voyager's trajectory doesn't necessarily intersect them. Over millions of years, the spacecraft might pass through one or two remnants, or it might avoid them entirely. Older supernova remnants are less hazardous. As a remnant ages, its shell expands and cools, and the radiation levels drop. Eventually, the shell merges with the interstellar medium, leaving behind only a diffuse cloud of enriched gas. If Voyager passes through one of these older remnants, the effect will be minimal, a slight increase in gas density, a modest uptick in radiation, but nothing catastrophic. Supernova remnants also contribute to the chemical enrichment of the galaxy. The explosion of a massive star produces heavy elements, carbon, oxygen, iron, and others which are ejected into space. These elements mix with the interstellar medium, providing the raw material for future generations of stars and planets. If Voyager encounters a supernova remnant, the spacecraft might be bathed in gas enriched with these elements, a testament to the recycling of matter through the galaxy. Some supernova remnants contain pulsars, the rapidly spinning neutron stars left behind after the explosion. Pulsars emit beams of radio waves that sweep across space like a lighthouse, and they can be detected from thousands of light years away. If Voyager passes near a pulsar, the spacecraft might be exposed to the pulsar's radiation, a beam of radio waves, X-rays, and gamma rays. The intensity of this radiation depends on the pulsar's orientation and distance, but in the worst case, it could be lethal to the spacecraft's remaining electronics. The magnetic fields inside supernova remnants are also much stronger than in the ambient interstellar medium. These fields are amplified by the shock front, which compresses and twists the magnetic field lines. If Voyager passes through such a region, the local magnetic field could be hundreds or even thousands of microgauss, far higher than the typical galactic value. This elevated field strength won't affect the spacecraft directly. Voyager is electrically neutral, but it will affect the motion of cosmic rays and the structure of the radiation environment. The search for Voyager's final resting place. Predicting where Voyager 1 will ultimately end up is one of the most challenging problems in celestial mechanics. The spacecraft's trajectory is shaped by countless forces: the gravity of the Sun, the pull of nearby stars, the tidal effects of the galaxy, the perturbations from molecular clouds. Each of these forces is small, but over millions of years they accumulate, making Voyager's path increasingly uncertain. Astronomers have attempted to calculate Voyager's future trajectory using computer simulations. These simulations model the gravitational field of the galaxy, the positions and motions of nearby stars, and the distribution of molecular clouds and other massive structures. The spacecraft's initial position and velocity are fed into the simulation, and the trajectory is calculated forward in time, step by step. The results are sobering. Over the first few thousand years, Voyager's path is relatively predictable. The spacecraft will continue to move away from the Sun, passing through the Oort cloud and into interstellar space. Its velocity will remain roughly constant, and its trajectory will curve slowly under the influence of the Sun's gravity and the galactic tide. But beyond a few thousand years, the uncertainties grow. The positions of nearby stars are known only to a limited precision, and their future motions are even less certain. A small error in a star's position or velocity can lead to a large error in the predicted time and distance of a close encounter, which in turn affects Voyager's trajectory. Over tens of thousands of years, these errors compound, and the predicted trajectory becomes a broad cone of possibilities. By 1 million years, the cone of uncertainty is so wide that Voyager could be almost anywhere within a region hundreds of light years across. Some simulations show the spacecraft drifting into the halo, rising thousands of light years above the galactic plane. Others show it remaining near the disk, crossing the plane multiple times as it oscillates. Still others show it being ejected from the galaxy entirely, flung into intergalactic space by a close encounter with a massive cloud or a passing star. The longest simulations, running for billions of years, produce even more diverse outcomes. In some runs, Voyager remains bound to the galaxy, orbiting the galactic center indefinitely. In others, it escapes, drifting through the void between galaxies. In a few runs, the spacecraft is captured by another star, becoming a permanent resident of a new solar system. The probability of each outcome depends on the details of the simulation and the assumptions about the galaxy's structure and evolution. One thing is certain: Voyager will not return to the solar system. The spacecraft's trajectory is hyperbolic relative to the Sun, meaning it has enough velocity to escape the Sun's gravity. Once it crosses the heliopause and enters interstellar space, it will never turn around. The Sun's pull will weaken with distance, and Voyager will continue to move outward, its path curving gently as the galaxy's gravity takes over. The spacecraft's final fate depends on the balance between its kinetic energy and the galactic potential. If Voyager's velocity is high enough, it will eventually escape the galaxy, reaching a point where the Milky Way's gravity can no longer hold it. The escape velocity from the galaxy, for an object in the Sun's orbit, is about 550 kilometers per second. Voyager is currently moving at only 17 kilometers per second relative to the Sun, and about 140 kilometers per second relative to the galactic center. This is well below the escape velocity, so the spacecraft is bound to the galaxy under current conditions. But conditions can change. A close encounter with a massive star or molecular cloud could boost Voyager's velocity, increasing its kinetic energy and pushing it closer to the escape threshold. A series of such encounters, each adding a small increment to the spacecraft's speed, could eventually provide enough energy to unbind Voyager from the galaxy. The probability of this happening is low, but it's not zero. If Voyager does escape the galaxy, it will drift into the local group, the collection of galaxies that includes the Milky Way, Andromeda, and dozens of smaller galaxies. The local group is gravitationally bound, so Voyager will remain within it, even if it leaves the Milky Way. The spacecraft might eventually approach another galaxy, perhaps Andromeda, or one of the dwarf galaxies orbiting the Milky Way, but the distances are vast and the timescales are enormous. It would take billions of years for Voyager to cross the void between galaxies, and by then, the spacecraft will be long dead, its components eroded, its power supply exhausted, the Golden Record's message to the stars. Voyager, one carries more than instruments and electronics, it carries a message. Bolted to the side of the spacecraft is the Golden Record, a 1-2-inch gold-plated copper disc containing sounds, images, and greetings from Earth. The record was designed as a time capsule, a snapshot of human civilization in the late 20th century, intended for any intelligent beings who might find it in the distant future. The record contains 115 images, encoded in analog form, showing scenes of life on Earth, landscapes, animals, people, architecture, and scientific diagrams. It also contains 90 minutes of audio, including greetings in 55 languages, natural sounds like wind, rain, and birdsong, and a selection of music from around the world, ranging from Bach's Brandenburg concertos to traditional songs from Africa, Asia, and the Americas. The record was created by a team led by Carl Sagan, who worked with artists, musicians, and scientists to curate its contents. The goal was to create a message that would be comprehensible to an alien intelligence, even one with no knowledge of human language or culture. The images include a diagram showing the record's playback instructions, as well as a pulsar map that indicates the position of the Sun relative to nearby pulsars, providing a cosmic address that can be decoded to locate Earth. But the golden record faces an uncertain future. Space is harsh, and the record is exposed to radiation, micrometeoroids, and the vacuum of space. The protective aluminum cover, coated with a thin layer of gold, shields the grooves from the worst of the radiation, but it won't last forever. Cosmic rays will gradually erode the gold coating, pitting the surface and exposing the aluminum underneath. Once the aluminum is exposed, it will oxidize, corroding and degrading the record's surface. The grooves themselves, etched into copper-plated nickel, are more durable, but they too will suffer. Cosmic rays will create defects in the copper, distorting the analog signal. The higher the cumulative radiation dose, the greater the distortion. Studies suggest the record might remain playable for a few 100 million years, but the quality will degrade over time. The audio will become noisy, filled with pops and crackles. The images will become pixelated, their details lost. Micrometeoroids pose another threat. A single impact from a grain of dust, travelling at tens of kilometers per second, could gouge a crater in the record's surface, destroying a portion of the grooves. The probability of such an impact is low, the record is small, and space is vast, but over millions of years, the cumulative risk becomes significant. Each impact will erase a bit more of the message, until eventually, nothing remains but a scarred, pitted disk. Yet the golden record's survival is not impossible. If Voyager avoids catastrophic encounters, if it passes through the galaxy without striking a comet, without being irradiated by a nearby supernova, without being captured by a star, the record might last for billions of years. In that case, it could outlive the Sun, which will exhaust its hydrogen fuel in about 5 billion years and expand into a red giant, engulfing the inner planets and rendering the solar system unrecognizable. If an alien civilization does find the record, what will they make of it? Will they understand the pulsar map, decoding Earth's position in the galaxy? Will they build a device to play the record, hearing the sounds of our world and seeing the images we chose to represent ourselves? Will they recognize the music, the laughter, the spoken greetings as signs of intelligence and culture? Or will they see only an artifact, a relic of a long-dead civilization, its message incomprehensible, its creators extinct? The golden record is a message in a bottle, cast into the cosmic ocean. Whether it ever reaches a shore, and whether anyone is there to read it, is a question we will never know the answer to. Dark matter interactions and invisible forces. Dark matter dominates the mass of the galaxy, yet it remains one of the most mysterious substances in the universe. It doesn't emit light, doesn't absorb light, and doesn't interact with electromagnetic radiation in any way we can detect. Its presence is inferred only from its gravitational effects, the way it shapes the rotation curves of galaxies, the motion of galaxy clusters, and the large-scale structure of the universe. Voyager 1 is travelling through a region filled with dark matter. The density of dark matter in the solar neighbourhood is estimated to be about 0.3 GeV per cubic centimetre, equivalent to roughly 1 proton mass per cubic centimetre. This is much higher than the density of ordinary matter in the interstellar medium, which is only about 0.001 proton masses per cubic centimetre. In other words, dark matter is hundreds of times more abundant than the gas and dust Voyager encounters. But despite this abundance, dark matter has almost no effect on the spacecraft. The leading candidates for dark matter are WIMPs, weakly interacting massive particles which interact with ordinary matter only through gravity and possibly through the weak nuclear force. The probability of a WIMP striking Voyager is vanishingly small, far lower than the probability of a micrometeoroid impact. If a WIMP did strike the spacecraft, the collision would be almost undetectable. WIMPs are thought to have masses ranging from a few GeV to hundreds of GeV, roughly the mass of a proton to the mass of a heavy atomic nucleus. A WIMP passing through Voyager might collide with an atom in the spacecraft's structure, transferring a tiny amount of energy. But the energy transfer would be so small that it would produce no measurable effect, no damage, no detectable signal. Yet dark matter's gravitational influence is significant. The dark matter halo surrounding the Milky Way shapes the trajectory of every object in the galaxy, including Voyager. As the spacecraft moves through the halo, it experiences the gravitational pull of the dark matter, which acts to keep it bound to the galaxy. This pull is weak, much weaker than the gravity of nearby stars or molecular clouds, but it accumulates over time. The distribution of dark matter in the galaxy is not uniform. It's densest near the galactic center and thins out with distance, forming a roughly spherical halo that extends far beyond the visible disk. Voyager's trajectory takes it through the lower halo, where the dark matter density is lower than average but still significant. Over millions of years, the cumulative gravitational pull of the halo will influence Voyager's orbit, causing it to curve and spiral as it moves through the galaxy. Some theories suggest that dark matter might not be entirely passive. Certain models propose that dark matter particles can interact with each other through new forces, creating structures and dynamics within the halo. If these models are correct, Voyager might pass through regions where dark matter is clumped into subhalos, dense concentrations of dark matter embedded within the larger halo. The gravitational pull of these subhalos could perturb Voyager's trajectory, adding another layer of unpredictability to the spacecraft's path. Another possibility is that dark matter decays or annihilates, producing a faint signal of radiation. If dark matter particles occasionally collide and annihilate, they might produce gamma rays, neutrinos, or other particles that could in principle be detected. If Voyager were still operational and equipped with the right instruments, it might detect these signals, providing direct evidence of dark matter interactions. But with its power supply exhausted and its instruments silent, any such signals will go unnoticed. The Milky Way-Andromeda collision and Voyager's fate. In about 4 to 5 billion years, the Milky Way and the Andromeda galaxy will collide, merging into a single, larger galaxy. This event will reshape the structure of both galaxies, scattering stars, disrupting orbits, and triggering bursts of star formation. Voyager 1, if it survives that long, will be a passive witness to this cosmic transformation. The collision will not be sudden. The two galaxies will approach each other over hundreds of millions of years, their dark matter halos overlapping long before their stellar disks touch. As they close the distance, tidal forces will begin to distort both galaxies, pulling long streamers of stars and gas into space. These tidal tails will stretch across hundreds of thousands of light years, glowing faintly as new stars form in the compressed gas. The first close pass will occur when the two galactic centers are only a few tens of thousands of light years apart. At this point, the gravitational interaction will be strong enough to disrupt the orbits of stars in both galaxies. Some stars will be flung out into intergalactic space, ejected by the violent gravitational slingshots. Others will be pulled inward, toward the merging cores. Voyager 1's fate during this collision depends on its position and velocity at the time. If the spacecraft is still near the outskirts of the Milky Way, it might be caught in one of the tidal tails, pulled outward by the gravitational tug-of-war between the two galaxies. In this scenario, Voyager could be ejected from the merged galaxy, cast into the intergalactic void. Alternatively, if Voyager is deeper within the Milky Way's halo, it might remain bound to the merged system. The spacecraft would continue to orbit the new galactic center, its path reshaped by the collision but not fundamentally altered. Over time, as the merged galaxy settles into a new equilibrium, Voyager would find itself in a different environment, an elliptical galaxy, with no spiral arms, no clear disk structure, just a smooth, featureless distribution of stars. The merger will also affect the Sunday. Our star, like most stars in both galaxies, will pass through the collision unscathed. The distances between stars are so vast that direct collisions are extremely rare. But the Sun's orbit will be disrupted, and it might end up in a completely different part of the merged galaxy. If Voyager is still relatively close to the Sun, within a few thousand AU, the spacecraft's trajectory will be influenced by the Sun's new orbit. More likely, Voyager will be far from the Sun by the time the collision occurs. The spacecraft will have drifted tens of thousands of AU away, possibly even light years, and the Sun's gravity will be too weak to affect it. Voyager will follow its own path, independent of the Sun, shaped only by the gravitational field of the merged galaxy. The collision will trigger a burst of star formation as gas clouds from both galaxies collide and compress. New stars will ignite across the merged system, creating bright regions of star formation visible from millions of light-years away. If Voyager passes through one of these regions, it might encounter elevated levels of radiation from the newborn stars, as well as increased densities of gas and dust. But the most dramatic consequence of the merger will be the coalescence of the two supermassive black holes at the centers of the Milky Way and Andromeda. These black holes, Sagittarius A star and M31's central black hole, will spiral toward each other, emitting gravitational waves as they merge. The final merger will produce a single, even more massive black hole, with a mass of about 100 million solar masses. Voyager will be far from this event, thousands of light-years away at least, and the gravitational waves will pass through the spacecraft without any detectable effect. But the merger will reshape the core of the new galaxy, and the intense radiation emitted during the final stages could sterilize nearby regions of space, destroying any planets or spacecraft unlucky enough to be too close. The heat death of the universe and Voyager's final silence. Long after the Milky Way-Andromeda merger, long after the last stars have burned out, Voyager 1 will still be drifting through space. But the universe itself will be changing, evolving toward a state of maximum entropy known as the heat death. Heat death is the ultimate fate of the universe, predicted by the laws of thermodynamics. In this scenario, the universe continues to expand, driven by dark energy, and all the available energy is gradually dissipated. Stars exhaust their fuel and die, leaving behind white dwarfs, neutron stars, and black holes. Galaxies merge and disperse, their stars scattering into the void. Eventually, even the black holes evaporate, releasing their mass as Hawking radiation over timescales of 10 to the power of 100 years. By the time the universe reaches the heat death, it will be cold, dark, and empty. The temperature will have dropped to just above absolute zero, and the density of matter will be so low that particles are separated by vast empty distances. No stars will shine, no planets will orbit, no galaxies will turn. The universe will be a featureless expanse, devoid of structure or complexity. Voyager 1, if it somehow survives that long, will be a relic of a bygone era. The spacecraft's structure will have long since eroded, its components scattered by collisions with micrometeoroids or degraded by radiation. The golden record will be unrecognizable, its grooves worn smooth, its message lost. Even the atoms that make up Voyager, the aluminum, the copper, the titanium, will begin to decay, as protons themselves eventually break down in the far, far future. But before that ultimate end, Voyager will have travelled unimaginable distances. Over trillions of years, the spacecraft will have crossed the galaxy, perhaps multiple times. It will have encountered countless stars, passed through molecular clouds, crossed supernova remnants, and drifted through the vast, empty regions between. It will have witnessed the birth and death of stars, the formation and dissolution of galaxies, the slow dance of cosmic evolution. And through it all, Voyager will remain silent, a passive observer, carrying its message from Earth into the deepening darkness. It is a message of curiosity, of exploration, of the human desire to reach beyond our world and touch the cosmos. Whether anyone ever hears that message, whether Voyager's journey ever finds an audience, is a question that may never be answered. But the journey itself, the act of sending a spacecraft into the unknown, of daring to explore the galaxy and beyond, is an achievement that transcends its ultimate destination. Voyager 1's journey is not just a physical odyssey through space. It's a testament to the human spirit, a symbol of our determination to understand the universe and our place within it. And as long as Voyager drifts through the cosmos, that message endures. The stellar nurseries and Voyager's passage through star-forming regions. The Milky Way is not a static collection of ancient stars, it's a living galaxy, continuously giving birth to new stars in vast molecular clouds scattered throughout its spiral arms. These stellar nurseries are among the most dynamic and energetic environments in the galaxy, regions where gravity compresses gas to such extreme densities that nuclear fusion ignites, creating the next generation of suns. Voyager 1's trajectory will eventually carry it near or through some of these regions, exposing the spacecraft to conditions radically different from the quiet interstellar medium it currently traverses. Star-forming regions are characterized by their extreme density. While the typical density of the interstellar medium is about 1 atom per cubic centimeter, The cores of molecular clouds can reach densities of 1 million atoms per cubic centimetre or higher. These dense cores are cold, with temperatures as low as 10 Kelvin, allowing hydrogen molecules to condense and clump together under their own gravity. When a clump reaches a critical mass, typically a few times the mass of the Sun, it begins to collapse, heating up as gravitational energy converts to thermal energy. The collapse process takes about 100,000 years for a Sun-like star, a rapid transformation by cosmic standards. As the core heats up, it begins to emit radiation, first in the infrared and eventually in visible light. When the core temperature reaches about 10 million Kelvin, hydrogen fusion ignites and a new star is born. The energy released by fusion creates an outward pressure that balances the inward pull of gravity, stabilizing the star and allowing it to shine for billions of years. But the birth of a star is a violent process. The collapse of the molecular cloud core generates powerful winds and jets that blast material outward at speeds of hundreds of kilometers per second. These outflows plow into the surrounding gas, creating shock waves that compress the material and trigger the formation of additional stars. The region becomes a churning cauldron of gas, dust, radiation, and newborn stars, each influencing the others in a complex dance of creation and destruction. If Voyager passes through a star-forming region, the spacecraft will encounter conditions unlike anything it has experienced before. The density of gas and dust will be thousands of times higher than in the ambient interstellar medium, increasing the probability of micrometeoroid impacts. The dust grains in molecular clouds are typically larger than those in the diffuse medium, up to a few micrometers in diameter, and they're sticky, coated with ices of water, carbon dioxide, and methane that can adhere to surfaces. The radiation environment in star-forming regions is also intense. Young, massive stars, those with masses 10 or more times that of the Sun, emit copious amounts of ultraviolet radiation that ionizes the surrounding gas, creating glowing regions called HII regions. The ultraviolet photons are energetic enough to break apart molecules, strip electrons from atoms, and heat the gas to temperatures of 10,000 Kelvin or more. If Voyager passes through or near an HII region, the spacecraft will be bathed in this intense radiation, which will accelerate the degradation of its materials. The magnetic fields in star-forming regions are also much stronger than in the general interstellar medium. Observations show that the fields in molecular cloud cores can reach strengths of 100 microgauss or more, about 30 times stronger than the typical galactic field. These fields play a crucial role in regulating star formation, supporting the clouds against gravitational collapse and channeling material onto the forming stars. The field strength affects the motion of cosmic rays and the propagation of shocks, creating a complex magnetized environment. One of the most dramatic features of star-forming regions is the presence of protostellar outflows and jets. As a star forms, it accretes material from the surrounding disk, and some of this material is ejected in narrow, high-velocity jets perpendicular to the disk. These jets can extend for light years, ploughing through the molecular cloud and creating bow shocks where they collide with ambient gas. The jets are composed of ionized gas moving at speeds of 100 to 500 kilometers per second, and they carry away angular momentum from the forming star, allowing the accretion to continue. If Voyager were to encounter one of these jets, an extremely unlikely event given their small cross-sectional area, the impact could be catastrophic. The jet's momentum flux would be enormous, potentially enough to damage or even destroy the spacecraft. But more realistically, Voyager might pass through the region affected by a jet, encountering enhanced densities, elevated temperatures, and turbulent motions in the gas. The timescale for Voyager to cross a star-forming region depends on the region's size and the spacecraft's velocity. Typical molecular clouds are tens to hundreds of light-years across, and at Voyager's speed of 17 kilometers per second, crossing one would take tens of thousands to hundreds of thousands of years. During this time, the region itself will evolve. Stars will form, mature, and begin to disperse the cloud with their radiation and winds. The cloud Voyager enters might be very different from the cloud it exits, transformed by the ongoing process of star formation. Star-forming regions are concentrated in the galactic disk, particularly in the spiral arms where gas is compressed by density waves. Voyager's trajectory, which oscillates above and below the plane, will carry it through the disk periodically, and during these crossings, the spacecraft has a higher probability of encountering a star-forming region. The exact probability depends on the coverage of such regions within the disk. Current estimates suggest that about 10% of the galactic disk's volume is occupied by molecular clouds. The passage through a star-forming region would leave no direct record. Voyager's instruments will have long since failed, and the spacecraft will be a passive, inert object by the time it encounters such regions, but the effects will accumulate on the spacecraft's structure. The increased flux of dust particles will erode the surface. The intense ultraviolet radiation will degrade polymers and coatings, and the elevated gas density will exert a drag force, however slight, that could minutely alter the trajectory. Some star-forming regions contain massive stars that will explode as supernovae within a few million years of their formation. If Voyager passes through such a region during this critical period, the spacecraft might be in the vicinity when one of these stars detonates. The consequences of a nearby supernova would depend on the distance at a few light years. The effects might be modest, just an increase in cosmic ray flux and a passing shock wave. At closer distances, the results could be far more severe. The study of star-forming regions has revealed that star formation is a self-regulating process. The energy and momentum injected by newborn stars through radiation, winds and supernovae heat and disperse the molecular cloud, eventually shutting off further star formation. This feedback process determines the overall efficiency of star formation in the galaxy, which is surprisingly low. Only about 1 to 3% of the gas in a molecular cloud actually ends up in stars. The rest is either dispersed or remains as diffuse gas. The galactic fountain and circulating gas flows. The Milky Way is not a closed system. Matter flows in and out of the galactic disk in a continuous cycle driven by stellar winds, supernova explosions, and gravitational interactions. This circulation of gas, known as the galactic fountain, plays a crucial role in the evolution of the galaxy, regulating star formation and distributing heavy elements created by dying stars throughout the disk and halo. Voyager 1, as it moves through the galaxy, will encounter these flows, passing through regions where gas is rising from the disk into the halo and falling back down in a perpetual rain. The galactic fountain begins with energy injection in the disk. Massive stars, through their intense radiation and powerful stellar winds, heat the surrounding gas to temperatures of millions of Kelvin. When these stars explode as supernovae, they release even more energy, creating expanding bubbles of hot gas that rise out of the disk under their own buoyancy. Multiple supernova explosions in the same region can merge their bubbles, forming superbubbles that can reach diameters of hundreds of light years. As these hot bubbles rise, they break through the cooler, denser gas of the disk and emerge into the halo. The gas in the bubbles' tenuous densities are typically only 0.001 atoms per cubic centimeter, but it's extremely hot, with temperatures reaching 10 million Kelvin. This hot gas emits X-rays, which have been detected by space telescopes like Chandra and XMM Newton, revealing the structure and extent of the galactic fountain. The hot gas rises to heights of several thousand light-years above the disk, before cooling and condensing. As it cools, it loses pressure and begins to fall back toward the plane under the influence of gravity. The infalling gas forms clouds and filaments that rain down onto the disk, replenishing the material lost to star formation and stellar winds. This cycle gas rises hot, cools in the halo, and falls back cold is the essence of the galactic fountain. The timescale for a complete fountain cycle is tens of millions of years. Gas ejected from the disk takes about 10 to 20 million years to rise, cool, and fall back. During this time, the gas travels distances of several thousand light years, moving through regions of widely varying density, temperature, and magnetic field strength. Voyager, on its own trajectory through the halo, might intersect these flows at various points in the cycle. If Voyager encounters a rising plume of hot gas, the spacecraft will experience elevated temperatures and reduced densities. The hot gas is so tenuous that it exerts almost no drag on the spacecraft, and the temperature, while high in terms of particle kinetic energy, doesn't translate to a high rate of heat transfer because of the low density. Voyager would pass through the plume essentially unaffected, though any functional instruments would detect the change in plasma properties. More significant would be an encounter with cold, infalling gas. These clouds, condensed from the hot fountain material, have temperatures of only 100 to 1000 Kelvin and densities up to 100 times higher than the ambient halo gas. The clouds move downward at speeds of 50 to 100 kilometers per second, driven by gravity and by the pressure of the surrounding hot gas. If Voyager's trajectory intersects one of these clouds, the spacecraft will experience a brief period of higher density and possibly collisions with dust grains mixed with the gas. The galactic fountain plays a critical role in the chemical evolution of the galaxy. The gas ejected from the disk is enriched with heavy elements, carbon, oxygen, iron, and others created by stellar nucleosynthesis and dispersed by supernova explosions. When this enriched gas returns to the disk, it mixes with the primordial gas, increasing the overall metallicity and providing the raw material for new generations of stars and planets. Observations of the fountain using radio and X-ray telescopes have revealed complex structures in the halo. The hot gas forms a network of interconnected bubbles and chimneys, channels through which material flows from the disk to the halo and back. These structures are not static, they evolve on timescales of millions of years as new supernovae inject energy, and as the flows respond to changes in the disk's star formation rate. One of the most prominent fountain structures is the Fermi bubbles, which we discussed earlier. These enormous lobes, extending 25,000 light-years above and below the galactic plane, may represent an extreme manifestation of the fountain process, possibly driven by an outburst from the central supermassive black hole rather than by stellar activity. The boundaries of the Fermi bubbles are sharp, suggesting that they were created by a discrete event rather than by continuous fountain flows. The galactic fountain also interacts with the circumgalactic medium, the diffuse halo of gas that surrounds the Milky Way. This medium, detectable through its absorption of light from distant quasars, contains a significant fraction of the galaxy's baryonic matter. The fountain feeds material into the circumgalactic medium, while infalling from the medium replenishes the disk, creating a complex exchange of matter between the galaxy and its surroundings. For Voyager, the fountain represents one of many dynamic processes that shape the galaxy's structure and evolution. The spacecraft's passage through fountain flows will be just one of countless encounters with galactic structures, each contributing incrementally to the spacecraft's long-term trajectory and fate. The fountain's influence on Voyager will be subtle, a slight change in velocity here, a dust impact there, but over millions of years, these subtle effects accumulate. The study of the galactic fountain has implications for understanding galaxy evolution more broadly. Many galaxies exhibit similar outflows, driven by star formation or active galactic nuclei. These outflows can regulate star formation by removing gas from the disk, or by heating the surrounding medium to temperatures too high for cooling and condensation. The efficiency of this feedback process determines whether a galaxy continues to form stars vigorously, or whether it quenches, becoming a red and dead elliptical galaxy. The fountain also demonstrates that galaxies are not isolated islands. They're embedded in a larger ecosystem that includes the circumgalactic medium, satellite galaxies, and the cosmic web. Matter flows between these components, driven by gravity, radiation, and kinetic energy. Voyager's journey takes it through this ecosystem, from the disk where it originated, through the halo where fountain flows circulate, and eventually perhaps to the boundaries where the galaxy merges with intergalactic space. Ancient stellar populations, and the galaxy's archaeological record. As Voyager 1 drifts through the Milky Way's halo, it will pass among some of the oldest stars in the galaxy, ancient red dwarfs, subdwarfs, and the remnants of stars that formed when the universe was less than 1 billion years old. These stellar fossils carry within their spectra the chemical signatures of the early universe, recording conditions that existed long before the Sun formed. Though Voyager cannot study these stars directly, its instruments will be silent. The spacecraft's trajectory through these ancient populations places it in the company of objects that have witnessed nearly the entire history of the cosmos. The oldest stars in the Milky Way are found primarily in the halo and in globular clusters, dense spherical collections of hundreds of thousands to millions of stars. These stars are metal poor, meaning they contain only trace amounts of elements heavier than helium. Astronomers measure metallicity using the ratio of iron to hydrogen, denoted as FeH. The Sun has Fe divided by H equals 0 by definition, representing the current abundance of iron in the solar neighbourhood. The oldest halo stars have FeH values of -4 or lower, meaning they contain less than 1/10,000th of the Sun's iron content. This metal poverty tells us that these stars formed from gas that had been enriched by only a few generations of massive stars. The very first stars in the universe, known as population 3 stars, contain no metals at all. They formed from primordial gas composed of only hydrogen and helium, the elements created in the Big Bang. These stars were massive, short-lived and explosive, ending their lives as supernovae that scattered the first heavy elements into space. The second generation of stars, including the oldest stars we can observe in the Milky Way, formed from gas enriched by these population 3 supernovae. The low metallicity of halo stars indicates they were born early in the galaxy's history, before many generations of stars had cycled through birth, life, and death. By studying their chemical compositions, astronomers can reconstruct the conditions in the early galaxy and learn about the properties of the first stars. Voyager's trajectory through the halo brings it into regions where these ancient stars are more common. The halo's stellar density is low, only about 1 star per cubic light year, compared to thousands per cubic light year in the galactic disk, but the stars that are present are predominantly old. Many are red dwarfs, small stars with masses of 10 to 40% of the Sun's mass. These stars burn their fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. Among the oldest stars in the halo are also white dwarfs, the cooling remnants of stars that exhausted their fuel billions of years ago. Some of these white dwarfs are so old and have cooled so much that they emit almost no light, detectable only through their gravitational effects or the faint infrared glow from their surfaces. These objects, sometimes called black dwarfs, though none have cooled enough to truly deserve the name, represent the endpoint of stellar evolution for low-mass stars. The distribution of ancient stars in the halo is not uniform. They're organized into streams and substructures, the remnants of smaller galaxies that were tidally disrupted and absorbed by the Milky Way. Each stream represents a distinct accretion event, a moment in the galaxy's history when it consumed another system. The stars in these streams share common orbital properties and chemical compositions, allowing astronomers to identify them and trace their origins. One of the most prominent stellar streams is associated with the Sagittarius Dwarf Elliptical Galaxy, which is currently being torn apart by the Milky Way's gravity. The stars from this galaxy form a vast, looping structure that wraps around the Milky Way multiple times, creating a complex pattern in the halo. Voyager's trajectory doesn't specifically target this stream, but given the stream's extent, there's a possibility the spacecraft could pass through it at some point in its journey. Another significant population is associated with the Gaia-Enceladus merger, a massive collision that occurred about 10 billion years ago. This event brought tens of billions of stars and vast amounts of gas into the Milky Way, fundamentally reshaping the galaxy's structure. The stars from Gaia-Enceladus are now spread throughout the halo, identifiable by their retrograde orbits, moving opposite to the general rotation of the galaxy and their distinctive chemical signatures. The chemical compositions of these ancient stars reveal the nucleosynthetic processes that operated in the early universe. Elements like carbon and oxygen are produced in massive stars through helium burning, while elements like iron are created in supernova explosions. The ratios of these elements in metal-poor stars provide clues about the masses and explosion mechanisms of the first supernovae, helping astronomers understand how the galaxy was chemically enriched over time. Some ancient stars show unusual abundance patterns, with enhancements of specific elements like europium or strontium. These patterns indicate that the stars formed from gas enriched by particular types of supernovae or by neutron star mergers, events that produce heavy elements through rapid neutron capture. The diversity of abundance patterns shows that the early galaxy was chemically heterogeneous, with different regions enriched by different sources. Voyager, passing among these ancient stars, is itself a very young object by cosmic standards. The spacecraft was built just a few decades ago, from materials that formed in the solar nebula 4.6 billion years ago. The atoms in Voyager's aluminum frame, its copper wiring, and its plutonium power source were created in stars that died before the Sun was born, scattered into space by supernovae, and eventually incorporated into the cloud of gas and dust that collapsed to form our solar system. The oldest stars in the halo have been shining for over 13 billion years, nearly as long as the universe has existed. They have witnessed the formation and evolution of the Milky Way, the merger of countless smaller galaxies, the birth and death of billions of stars. Voyager, by contrast, is a momentary visitor, a fleeting presence that will pass through the halo and move on, leaving no trace. Yet in another sense, Voyager is part of the same cosmic story. The spacecraft is made from stardust, assembled by beings who are themselves made from stardust, sent on a journey through a galaxy shaped by billions of years of stellar death and rebirth. The ancient stars and the modern spacecraft are connected by the same thread, the continuous recycling of matter that has built the universe's complexity from the simple ingredients of the Big Bang, gravitational microlensing, and Voyager's chance alignments. As Voyager 1 travels through the galaxy, it will occasionally pass near stars whose gravitational fields are strong enough to bend the light from even more distant stars, creating a phenomenon known as gravitational microlensing. These chance alignments, predicted by Einstein's general theory of relativity, occur when a foreground star, the lens, passes nearly in front of a background star, the source, and the gravitational field of the lens bends and magnifies the source's light. For a brief period, days to months, the background star appears to brighten, creating a characteristic light curve that can be detected by telescopes. From Earth, astronomers use microlensing to study dark objects like rogue planets, brown dwarfs, and stellar mass black holes that don't emit their own light. The technique has also been used to detect exoplanets orbiting the lens stars, as the planets create additional spikes in the light curve when they too act as lenses. Thousands of microlensing events have been observed, revealing the hidden population of dark objects in the Milky Way. Voyager itself could in principle act as a lens. Though the spacecraft is tiny compared to a star, any object with mass creates a gravitational field that bends light. The amount of bending depends on the mass and the geometry of the alignment specifically. The Einstein radius, the separation between the lens and the source at which the light bending is maximized. For an object of Voyager's mass about 825 kilograms, the Einstein radius is incredibly small, roughly the size of an atom when viewed from Earth. This means that for Voyager to produce a detectable microlensing effect, the background star would have to be aligned with the spacecraft to a precision of better than 1/1,000,000th of an arcsecond, and even then, the magnification would be negligible. No existing or planned telescope could detect such an event, but Voyager could be near a microlensing event produced by a star. If the spacecraft happens to be in the vicinity of a lens star during an event, it might pass through the region where the background star's light is being focused. This region, called the lensing caustic, is where the magnification is highest and where the light from the background star converges. The size of the lensing caustic depends on the masses of the lens and source stars and the distances between them. For typical stellar masses and distances of kiloparsecs, the caustic can be hundreds of AU across roughly the size of our solar system. If Voyager passes through this region, it would be bathed in focused starlight, potentially orders of magnitude brighter than the light from the lens star itself. The intensity of this focused light would depend on Voyager's exact position within the caustic. Near the center, where the magnification is highest, the flux could be 100 to 1,000 times the normal intensity. Farther from the center, the magnification decreases, and the flux drops to more typical levels. The duration of the enhancement depends on Voyager's velocity and the size of the caustic at 17 kilometers per second. The spacecraft might cross the caustic in a few days to a few weeks. The effects of this intense illumination on Voyager would be minimal. The spacecraft is designed to operate in the sun's intense radiation at close range, and even a 1,000-fold enhancement of a distant star's light would be far less intense than sunlight at Earth's orbit. The golden record might experience a slight warming, and any residual coatings or materials on the spacecraft's surface might undergo photochemical reactions, but there would be no catastrophic damage. However, if Voyager's instruments were still functional, an impossibility given the spacecraft's limited power supply, they could potentially detect the lensing event by measuring the change in the background radiation field. The spacecraft's photometers and spectrometers, if operational, could observe the brightening of the background star and record its spectrum, providing data on the star's properties and the geometry of the lensing configuration. The probability of Voyager being near a microlensing event is extraordinarily low. Microlensing events are rare. Only about one star in a million is lensing another at any given time, and the lensing caustic occupies only a tiny fraction of space. For Voyager to pass through a caustic, it would need to be in exactly the right place at exactly the right time, a coincidence so unlikely that it's essentially impossible. Yet impossible doesn't mean zero probability. Over millions of years, as Voyager drifts through regions containing billions of stars, the cumulative probability of encountering at least one microlensing event increases. It remains small, perhaps one chance in billions, but not zero. More likely is that Voyager will pass near stars that are themselves acting as lenses, bending the light of even more distant background stars. From the spacecraft's perspective, these events would be invisible. The bending occurs along the line of sight from the observer to the stars, and Voyager, being off to the side, wouldn't see any unusual effects. But the spacecraft would be sharing space with a star that is, at that moment, creating a gravitational mirage visible from Earth. The study of gravitational microlensing has revealed important information about the distribution of mass in the galaxy. By analysing the frequency and duration of lensing events, astronomers can estimate the number of dim stars, brown dwarfs, and even rogue planets drifting through the Milky Way. These surveys have shown that there may be billions of Jupiter-mass objects that aren't bound to any star, ejected from their birth systems during planetary formation. Voyager itself is in a sense a rogue spacecraft unbound from its parent star, drifting through the galaxy on an independent trajectory. The spacecraft shares the void with these rogue planets, all of them moving through the darkness, invisible except for the occasional gravitational interaction. The concept of gravitational lensing extends beyond individual stars. On larger scales, the mass of entire galaxies and galaxy clusters can lens the light from even more distant galaxies, creating dramatic arcs and multiple images visible in deep space telescopes like Hubble. These strong lensing events have been used to study the distribution of dark matter and to probe the properties of distant galaxies that would otherwise be too faint to observe. Voyager will never be close enough to such a massive lens to experience its effects directly, but the spacecraft is travelling through a universe where space-time is constantly being warped by the gravitational fields of massive objects. Every star, every planet, every galaxy creates a curvature in space-time, and Voyager's trajectory is shaped by the combined effect of all these curvatures, integrated over the immense distances it travels. The influence of passing molecular clouds on Voyager's trajectory. Throughout its journey across the galaxy, Voyager 1 will encounter not just individual stars, but also giant molecular clouds, vast diffuse structures of cold gas and dust that span hundreds of light years. These clouds are among the most massive objects in the Milky Way, with masses ranging from thousands to millions of solar masses. Their gravitational influence extends far beyond their visible boundaries, and a close passage by one of these clouds could significantly alter Voyager's trajectory in ways that are difficult to predict. Molecular clouds are the birthplaces of stars, but they're also gravitational obstacles that perturb the orbits of passing objects. The clouds are composed primarily of molecular hydrogen, with temperatures typically between 10 and 50 Kelvin. At these low temperatures, the gas moves slowly, and the clouds are held together by their own gravity rather than by thermal pressure. The densest regions, called molecular cloud cores, can have densities of millions of particles per cubic centimetre, while the diffuse outer regions have densities closer to a few hundred particles per cubic centimetre. The total mass of a giant molecular cloud can exceed 1 million solar masses, making it comparable to a small galaxy. This enormous mass creates a substantial gravitational field that can influence objects passing nearby. The gravitational potential of a cloud extends well beyond its visible edge, creating a zone of influence that can be hundreds or even thousands of light years across. When Voyager approaches a molecular cloud, the spacecraft will begin to feel the cloud's gravitational pull long before it enters the cloud itself. The force will be weak initially, but it will grow as the spacecraft gets closer. Depending on the geometry of the encounter, whether Voyager passes in front of, behind, or through the cloud, the gravitational interaction will either accelerate or decelerate the spacecraft, and it will deflect the trajectory by some angle. The magnitude of the deflection depends on several factors: the mass of the cloud, the closest approach distance, and Voyager's velocity relative to the cloud. For a cloud of 1 million solar masses and a closest approach of 50 light-years, the deflection angle would be on the order of a few arc-minutes, and the change in velocity could be several meters per second. This might seem small, but over millions of years such changes accumulate and can significantly alter Voyager's path through the galaxy. If Voyager actually enters a molecular cloud, the effects become more complex. Inside the cloud, the density of gas and dust is much higher than in the ambient interstellar medium, and the spacecraft will experience drag as it plows through the material. The drag force is proportional to the density and to the square of the velocity. So even though the density inside a cloud is still very low by terrestrial standards, the cumulative effect over thousands of years can be measurable. The drag will cause Voyager to lose kinetic energy, gradually slowing down as it passes through the cloud. The amount of deceleration depends on the density profile of the cloud and the length of the path through it. For a cloud with an average density of 1,000 particles per cubic centimetre and a path length of 100 light-years, Voyager might lose a few meters per second of velocity again, a small but non-negligible effect. The cloud's magnetic field will also play a role. Molecular clouds are threaded with magnetic fields, typically with strengths of 10 to 100 microgauss. These fields are much stronger than the typical interstellar field and can affect the motion of charged particles within the cloud. Voyager itself is electrically neutral, so the magnetic field won't exert a direct force on the spacecraft, but the field does influence the distribution of cosmic rays and the structure of the plasma within the cloud. One of the most interesting aspects of molecular cloud encounters is their stochasticity. The clouds are distributed irregularly throughout the galaxy, concentrated in the spiral arms but present in other regions as well. The locations and motions of the clouds change over time as they form, evolve, and disperse, making it impossible to predict exactly when and where Voyager will encounter one. Each encounter is a random event, adding an element of unpredictability to the spacecraft's long-term trajectory. Computer simulations of Voyager's trajectory attempt to model these encounters by including statistical distributions of molecular clouds in the galaxy. The simulations use observed properties of clouds, their masses, sizes, and spatial distribution to estimate the probability of encounters and their effects. The results show that over a few million years, Voyager is likely to encounter at least one giant molecular cloud, and possibly several. Each encounter will perturb the trajectory in a slightly different way, depending on the specific properties of the cloud and the geometry of the approach. Over time, these perturbations will cause Voyager's path to diverge from any deterministic prediction, making the spacecraft's long-term trajectory essentially chaotic. This doesn't mean the trajectory is random in an absolute sense. It's still governed by the laws of physics, but it does mean that small uncertainties in the initial conditions or in the properties of the clouds can lead to large differences in the final outcome. The gravitational effects of molecular clouds are not limited to Voyager. These clouds play a crucial role in shaping the structure and evolution of the galaxy. Their gravity can trigger the formation of new stars by compressing nearby gas, and their tidal forces can disrupt passing star clusters and stellar streams. The clouds also act as gravitational reservoirs, storing mass in the disk and influencing the overall gravitational potential of the galaxy. Some molecular clouds are associated with star-forming regions, where massive stars have already begun to form and are dispersing the cloud with their radiation and winds. These regions are more hazardous for Voyager because they contain not only the cloud itself, but also young stars emitting intense ultraviolet radiation, expanding HII regions, and possibly supernova remnants from massive stars that have already exploded. If Voyager passes through one of these active regions, the spacecraft will be exposed to a complex environment with elevated radiation levels, higher densities, and strong magnetic fields. The cumulative effect of these conditions could accelerate the degradation of the spacecraft's materials and alter its trajectory through a combination of gravitational and non-gravitational forces. On the other hand, if Voyager encounters an older, quiescent molecular cloud, one that has not yet formed many stars or has already dispersed most of its massive stellar population, the environment will be more benign. The cloud will still exert a gravitational influence, but the radiation levels will be lower, and the density variations will be less extreme. Rogue planets and the dark population of the Milky Way. Between the stars, drifting silently through the darkness, are billions of objects that shine no light of their own rogue planets, ejected from their birth systems during the chaotic process of planetary formation. These orphan worlds, unbound from any star, wander the galaxy on independent trajectories, invisible to telescopes except when they pass in front of a background star, and create a brief microlensing event. Voyager 1, as it travels through the Milky Way, shares the void with these dark nomads, and there's a small but finite possibility that the spacecraft could pass near one of them. Rogue planets are thought to form in protoplanetary disks around young stars, just like the planets in our solar system, but during the early, violent phase of planetary system formation, gravitational interactions between planets can eject some of them from the system entirely. Computer simulations of planetary dynamics show that for every stable planetary system like our own, several planets are likely to have been ejected, flung into interstellar space at velocities high enough to escape the star's gravity. The population of rogue planets in the Milky Way is poorly constrained, but estimates based on microlensing surveys suggest there could be as many rogue planets as there are stars, perhaps 100 billion or more. These objects range in size from Mars mass to several times Jupiter's mass, with the most common being super-Earths and Neptune-mass planets. Some may have formed as planets and been ejected, others may have formed directly from the collapse of gas clouds, blurring the line between planets and brown dwarfs. A rogue planet, lacking the warmth of a parent star, would be an incredibly cold, dark world. Its surface temperature would be determined only by its internal heat, the residual warmth from its formation, plus heat generated by radioactive decay in its core. For a Jupiter-mass planet, this internal heat could maintain a surface temperature of around 100 Kelvin for billions of years, warm enough to sustain a thick atmosphere and possibly even subsurface oceans if the planet has enough internal heating. Smaller rogue planets, like Earth-mass worlds, would cool more quickly, their surface temperatures dropping to near the cosmic microwave background temperature of 3 Kelvin within a few tens of millions of years. These frozen worlds would be coated in layers of solid nitrogen, methane, and water ice, their atmospheres collapsed onto the surface as snow. Any life that might have existed on such a world before its ejection would almost certainly perish in the deep freeze of interstellar space. The probability of Voyager encountering a rogue planet depends on the spatial density of such objects and the cross-sectional area of interaction. If there are 100 billion rogue planets in the Milky Way, and they're distributed relatively uniformly throughout the disk and halo, the average separation between them would be about 1 or 2 light-years. Voyager, travelling at 17 kilometers per second, would take tens of thousands of years to cross that distance. But encountering a rogue planet doesn't mean colliding with it. The probability of a direct collision is vanishingly small. The cross-sectional area of even a Jupiter-sized planet is tiny compared to the vast distances of space. Instead, an encounter would mean passing within a few AU or a few light days of the planet, close enough for the planet's gravity to perturb Voyager's trajectory. For a Jupiter-mass planet and a closest approach of 1 AU, the gravitational deflection of Voyager's trajectory would be only a few arc minutes, and the change in velocity would be a few meters per second detectable in principle, but small compared to the perturbations from stellar encounters or molecular clouds. For a smaller planet, say Earth mass, the effect would be even weaker, probably undetectable even if we were monitoring Voyager's trajectory with perfect precision. The more intriguing scenario is a very close encounter within a few million kilometers. At such distances, the planet's gravity would become the dominant force, and Voyager could be deflected significantly or even captured into orbit. Capture is unlikely because Voyager's velocity relative to the planet would typically be tens of kilometers per second, well above the planet's escape velocity. But in a three-body interaction, if Voyager, the planet, and a nearby star all interact simultaneously, energy could be transferred in ways that leave Voyager bound to the planet. If Voyager were captured by a rogue planet, the spacecraft would become a satellite of that world, orbiting it indefinitely in the darkness of interstellar space. The orbit would likely be highly eccentric, and over time, tidal forces from passing stars could perturb it, potentially ejecting Voyager again, or causing it to crash into the planet's surface. The detection of rogue planets is one of the frontiers of exoplanet science. Microlensing surveys have found a handful of candidates, but the technique is limited. It can only detect planets when they happen to pass in front of a background star, a rare geometric alignment. Future missions, like the Nancy Grace Roman Space Telescope, will conduct wide-field microlensing surveys that could detect thousands of rogue planets, constraining their population and properties. Some rogue planets might be detectable by their thermal emission in the infrared. A young, massive rogue planet, say, a few times Jupiter's mass and less than 1 billion years old, could still be glowing from its formation heat, emitting enough infrared radiation to be detected by sensitive telescopes like JWST. These warm rogues would be rare, but finding even a few would provide valuable insights into the planet formation and ejection processes. Another possibility is that some rogue planets are not truly alone. They might be accompanied by moons. Just as Jupiter has dozens of moons, a rogue gas giant could retain its satellites after ejection, creating a miniature planetary system adrift in interstellar space. Tidal heating from the planet's gravity could keep these moons warm, possibly maintaining subsurface oceans for billions of years. Such systems, though speculative, have been proposed as potential habitats for life in the absence of a star. Voyager's passage through a galaxy filled with rogue planets is a reminder of the richness and complexity of the interstellar medium. Space is not empty. It's populated by stars, planets, gas clouds, dust, and countless other objects, all moving on their own trajectories through the gravitational landscape of the Milky Way. Voyager is just one more object in this vast dynamic system, its path shaped by the same forces that govern everything else. The existence of rogue planets also raises philosophical questions about the nature of planetary systems and the definition of a planet. Is a planet still a planet if it doesn't orbit a star? Does the context of its environment matter, or is planehood defined by intrinsic properties like mass and composition? These questions, while abstract, have practical implications for how we classify objects and understand the diversity of worlds in the galaxy. For Voyager, the distinction is moot. The spacecraft will drift past stars, planets, and clouds without preference, responding only to the gravitational forces they exert. Whether an object is classified as a star, a planet, or something else is a human construct, irrelevant to the physics that governs Voyager's journey.